Good afternoon, ladies and gentlemen. Today's topic that I'll be discussing is sample size determination, parameters, and pitfalls. We shall be following this outline for this presentation. I'll begin with an introduction. I will also discuss why sample size determination is important. We will consider the key parameters in sample size determination. We'll also look at the common pitfalls and consequences and explore practical strategies and tools for mitigating these pitfalls. We'll then conclude with a question and answer section. Research involves the observation of a sample from some predetermined or predefined population of interest. We then draw conclusions from that study based on generalizing the results we got from the sample to the entire population from which the sample was drawn. The accuracy of our conclusions will depend on two things. The first of which is how the samples were collected, and the second of which is how representative the sample is of the population. An understanding of the basic statistical concepts of hypothesis testing, significance level, and power is essential for a discussion of sample size estimation. What is sample size determination? It is the statistical process of estimating the number of participants needed to detect an effect accurately. Sample size determination is very important in research for two main reasons. First of which is, if the sample is too small, we have a greater risk of having false negatives. There is also the possibility that we would waste resources to carry out a study. If the sample is too large, on the other hand, then ethical questions may arise because we might find that we have exposed a greater number of people than we ought to some unforeseen risk of the research that we are carrying out. Not to talk of inflated costs or increased costs that come with larger sample sizes. Our goal, therefore, today is to understand the parameters that determine the sample size, to avoid pitfalls, and to learn how to apply best practices. What is a population? What is a sample? A population consists of all members of a defined group, whereas a sample is a subset of the entire population. And so when we talk about population, we talk about parameters. And when we talk about samples, we talk about statistics. So when we hear the word statistics, we're essentially referring to the sample. And the whole goal of our research is to try to infer what population parameters are from the sample statistics. So we try to infer what the true population mean would be, or what the true population standard deviation will be, or what the true prevalence of a particular condition or outcome would be in the population. We also need to know what a null hypothesis is and what the alternative hypothesis is. The null hypothesis is a statement that declares that what we have observed is entirely due to chance. In other words, what we find in our sample is completely due to chance. So that is the null hypothesis. And this is the hypothesis that the researcher hopes to reject. On the other hand, the alternative hypothesis is the opposite of the null hypothesis. It is the hypothesis the researcher hopes to bolster. A type 1 error occurs when we reject a true null hypothesis. And related to this concept of type 1 error are the terms alpha and confidence. Our alpha is the probability of committing a type 1 error. That is to say, the probability of us rejecting a true null hypothesis. The confidence is the complement of alpha, and that is the probability of not committing a type 1 error. A type 2 error is when we retain an incorrect null hypothesis. In other words, we fail to reject a false null hypothesis. Related to this concept are the terms beta and 1 minus beta. The probability of a type 1 error is beta. And like I've pointed out, it is the probability of retaining a false null hypothesis. The complement of beta is what we know as power. So when we calculate sample size and we talk about power, we're essentially talking about the probability of not committing a type 2 error. In other words, the probability of not rejecting a false null hypothesis. What is sampling? It is the process of choosing a subset of the population for observation and for study. We do sample because it is impractical to measure an entire population. So, for example, if a researcher was trying to study the prevalence of breast cancer in Nigerian women, it would be impossible and impractical to measure all the women in Nigeria. And sampling helps us to reduce cost, time, and the number of personnel needed to carry out the research. It must be noted that the sample should be representative of the population as a whole. And the predictive power of any study is based on both the sample size and the quality of the sampling method. We need to understand that the whole field of statistics is based on the assumption that the sample was randomly selected from the population. And so the key word there is that the sample should be randomly selected. Why does sample size matter? It matters because there are real-life consequences. If the study is too small, then it lacks power. And if it lacks power, it will be unable to detect any true effect that is present. And so in a drug trial, the researcher may fail to find that the drug is effective because the sample is too small. On the other hand, if the sample is too large, then there's unnecessary risk. So, an ethical balance needs to be struck. There are 5 big drivers of sample size: effect size, significance level, statistical power, variability, and population and design factors. These 5 parameters are very important in any determination of sample size. The first parameter is effect size, often represented by the Greek letter delta. What is it? It can be defined as the minimum clinically meaningful difference that the researcher is interested in ascertaining. So, for example, we could have a 10% reduction in blood pressure or a 5 kilogram reduction in weight. The problem we often have sometimes is optimism bias. The researcher may end up overestimating the effect size, and in doing so, will end up with a study that is undersized. How do we mitigate this pitfall? By using pilot data or literature. We should also understand how to ascertain the size of an effect using Cohen's conventions. So, calculating Cohen's d will tell us whether the effect that we're interested in is small, medium, or large. A small effect size is 0.2 and below, and between 0.2 and 0.5 we consider that effect size to be medium. A large effect size would be from 0.8 and above. The second parameter is significance level, which we represent using the letter alpha. Again, to reiterate and recap, this is the probability of committing a type 1 error. Typically, we set alpha as 5%. Once again, a potential pitfall occurs when we are carrying out multiple tests or multiple comparisons. The more statistical comparisons we are carrying out, the more likely we are to commit a type 1 error. So for example, if you carried out 20 tests and you set your alpha at 0.05, there is a 64% probability of committing a type 1 error. And so, what is the practice to mitigate this? You adjust your alpha for multiple comparisons, and there are several different methods to do so. But one of the commonest well-known ones is using the Bonferroni method, and that typically just divides alpha by the number of comparisons that are being done. Third parameter is power, 1 minus beta. It is the probability of detecting an effect if it is real. We typically set our power at 80 to 90%. One of the common pitfalls is setting the power too low, especially for trials where the outcome is very important. So for example, high stakes trials like cancer drugs, you probably would need to set the power a bit different. So what do we need to do to mitigate this? We have to set higher power for pivotal trials. Variability. The standard deviation of the outcome is a statistical measure of the variability, and this is represented by sigma. Sigma squared is the variance of variability. Again, one of the common pitfalls is to underestimate the sigma, and doing so often leads to an undersized study. Again, the best practice to mitigate this is to use a worst case alpha from a pilot or literature review. Could also do some pre-test measures as well. And so you see that the pilot study that we sometimes mention plays an important role in helping to get information to calculate sample sizes. The fifth one is population and design factors. And there are key factors here, depending on the kind of study that's being done. For example, if it's a randomized clinical trial, you want to consider your allocation ratio. Are the groups equal or are they unequal? For example, you might have a group where you have twice as many people as the other group. This will contribute to the total sample size. You also want to consider attrition dropout, or loss to follow-up. And typically we try to correct for this by adjusting the sample size to account for loss of attrition. Loss to follow-up or attrition. Typically, you want to add a 10 to 20% adjustment. You also need to account for clustering. For example, if you have multi-center trials, or even trials that measure repeated measurements over a period of time, you want to adjust for what is known as intra-cluster correlation, because you will find that groups of people tend to be similar, or measurements, repeated measurements in a single individual tend to be correlated, and so this needs to be adjusted for. The mitigation strategy for that requires design-specific tools. T-test, ANOVA, regression, survival analysis, so on. So, let us review the common pitfalls that occur when we calculate sample sizes. The first one is what I would call garbage in, garbage out. Poor parameter estimates lead to flawed sample size. For example, you are using a delta of 0.5 without justification. This can result in a 64% power if the true delta is 0.3. So how do we fix this? We fix this by carrying out a sensitivity analysis, and then we test what the sample size is across a number of ranges determined by delta over sigma. In other words, the delta divided by the standard deviation. The second pitfall is to ignore attrition, dropout, or loss of follow-up. So if, for example, you have a 20% dropout rate, your effective power will drop from 80% to 66%. The fix for that is to adjust the sample size using the formula as indicated. And in this case, it's the calculated sample size divided by 1 minus R0 minus Ri, where R0 is the dropout rate and Ri is the drop-in rate. Because in some studies, you may have people coming in and leaving. That can happen, and that also needs to be accounted for. The third pitfall is misaligned analysis. You are calculating N, or rather sample size, for t-test, whereas the analysis you are going to do requires regression. This often leads to biased results. And so how do we fix that? We match the sample size calculation to the planned analysis. So for example, if we are going to study greater than 2 groups, we're going to use an ANOVA, and so we need to calculate the sample size to account for that. The fourth common pitfall is what I call magical defaults. So you're blindly using alpha 0.05 and power 80%. This itself can lead to ethical or scientific failure. There have been clinical trials that have been halted for futility after resources were expended. And the fix for that is to justify all parameters contextually. So if you're going to use an alpha of 0.05, it needs to be justified. And whatever power you choose, you also need to justify it. What are the practical strategies? You need to set up a step-by-step workflow. The first step is to define your primary endpoint. The second step is to estimate your delta or your effect from your literature or from a pilot study. The next step, or the third step after that, is to set your alpha or your type 1 error rate. And here you need to make sure you adjust for multiple comparisons. So if you are going to do multiple comparisons, you need to adjust your alpha accordingly. The fourth step is to choose your power. If you are interested in an outcome that is really, really important or has significant implications, then you want to choose your power to be higher than the usual 80%. Then you want to estimate your variability of variation conservatively. And then you need to add your attrition buffer. In other words, you need to adjust for loss to follow-up or attrition rate. And then the last step is you validate what you have done with software. Again, typically these days, we do not calculate these things manually. There are all sorts of tools and software that are available, a lot of them free, which we can use to calculate or determine our sample size. We have tools like OpenEpi, GPower, the PWR package in R, statistical software, and even power and sample size calculation, which is a website where you can calculate your sample sizes. There are other tools which are available but are commercial: Stata, Parse, SAS, mQuery. When do you need to consult a statistician? When you are dealing with complex designs. So there is some sort of cluster randomization, you think you're going to do some Bayesian statistics, you have repeated measures, you expect that data will be missing, you are submitting for regulatory approval, NAFDAC, FDA, whatever. One thing you need to know is this: you need to involve your statisticians early at the planning stages and not after you have collected your data. The main determinant of the sample size is how accurate the results need to be. And this depends on the purpose of the study. A descriptive study determines a summary measure of a characteristic, while in an analytical study, specific sets of hypotheses are being tested. And so we come to this point where we look at sample size for descriptive study. The main objective is to obtain an estimate of a population parameter. For example, the proportion of people who smoke, or the average daily caloric intake of the population. The sample size required to answer these questions depends on several factors. For example, measure of interest, the underlying probability distribution, the sampling distribution of the measure, and the desired level of accuracy. We need to note this, that most research questions fall into one of two possible scenarios: the binomial distribution, when one wants to estimate the proportion of a certain event or outcome or characteristic, and the normal distribution, when one wants to estimate an average value. So that's what we mean when we say the underlying probability distribution. So it's either binomial, so we're estimating proportions, or it's a normal distribution because we want to estimate an average value. Here's an example. Suppose we want to conduct a survey to determine the prevalence of a relatively common disease in a community. We want to determine how many people should be observed to obtain a reasonably accurate picture of the prevalence. We can see the sample size formula displayed. So the problem is to calculate the sample size required for estimating the prevalence of the disease within plus or minus 5% of the true value with 95% confidence. So we specify the coefficient 1 minus alpha to be 95%. That's the confidence to be 95%. We fix the width of the interval delta to be 10%. You may ask, where did the 10% come from? plus or minus 5% gives us a range of 10%. We make a guess as to the value of the prevalence as 30%. And so if we plug in this into the formula, we end up with a sample size of 323. Thus, we need a minimum of 323 subjects observed to assure that the 95% confidence interval for the estimated proportion will be within 5% of the true prevalence. Please note that we do not know the true prevalence. We are only trying to hazard a guess as to what the true prevalence is. So you would see from the foregoing that even in a cross-sectional study, the calculation of the sample size has embedded within it an implicit form of hypothesis testing, because we are talking about alpha, the probability of committing a type 1 error, which in this case is estimating what we think the true population prevalence will be, and saying whatever we get from our sample is not different from the true population parameter within a certain level of confidence. And so this lets us know that statistical hypothesis is a little bit different from the research hypothesis. The calculation we just demonstrated assumes a random sample from a relatively large population. Sometimes the population from which the samples are drawn may be fixed and small. An example of that would be we're carrying out some survey on all doctors within a particular locality. That is an example of a finite population. And in such cases, corrections to the previously shown formula are required. And the formula for that is once again displayed on the screen. DEF is the design effect. N, capital N, is the population size. And Q hat is 1 minus P hat, where P hat is the prevalence that we're assuming we want to find. So this formula helps us to calculate. And so this is the finite population correction factor, as is sometimes known. What of if we are interested in estimating a population average? Suppose we want to estimate the average daily caloric intake of people in a community. The sample size formula is displayed, and we can see here that the daily caloric intake is assumed to have a normal distribution around mu, which is the population mean, with a standard deviation sigma. The problem is to calculate the sample size required for estimating the average daily caloric intake within plus or minus 25 calories of the true value with 95% confidence. So we specify the parameters. So our confidence coefficient again is 95%. The width of the interval that we're interested in is 50 calories. And we obtain the standard deviation as 150 calories. And plugging all this into the formula gives us a sample size of 35. Thus, we need a minimum of 35 subjects observed to assure that the 95% confidence interval for the estimated average daily caloric intake will be within plus or minus 25 calories of the true population average. What about sample size for analytical studies? Recall that the primary purpose of an analytical study is to test a null hypothesis. The sample size calculations require the specification of the limits of the type 1 and type 2 errors. One also has to determine the sample measures that will be used. Is it a proportion, a mean, or an estimate of relative risk or odds ratio, and their associated sampling distributions? Suppose we're testing equality of two proportions. The sample measures used are the sample proportions. The sampling distribution used in testing this null hypothesis is either the standard normal distribution Z or, equivalently, the chi-square. And thus, we see the formula that is to be used for this sort of studies. Note that P hat represents the pooled prevalence, which is P1 plus P2 divided by 2. The calculation of a type 2 error, or beta, depends on a precise definition of null hypothesis is not true. The simplest way to do this is to define the smallest difference in the two proportions that we consider meaningful, that is, what we consider to be clinically significant, and calculate beta under this hypothesis. So here is a little example to illustrate this concept. We're interested in determining the sample size required in a clinical trial of a new drug that is expected to improve survival. Suppose the traditional survival rate is 40%, that is, P2 is 0.4. We're interested in detecting whether the new drug improves survival by at least 10%, that is, delta is equal to 0.1. The first step is to specify the parameters. So the first step of that is to set the type 1 error, alpha, as 0.05. And therefore, that gives us a Z score of 1.96. We next need to determine that the minimum clinically significant difference, delta, is 0.1. And then we make a guess as to the proportion in one group, usually the control. So in this case, P1 is 0.4, therefore P2 is 0.5. We need to determine the power required to detect the difference. And since we pick a power of 95%, that gives us a Z beta of minus 1.645. If we plug these values into the equation that we displayed earlier, it gives us a sample size of 640. Thus, the study will require 640 subjects in each of the two groups to assure a probability of detecting an increase in the survival rate of 10% or more with 95% certainty, if the statistical test used 5% as the level of significance. What if we want to compare two population means? The sampling distribution of the difference of the sample means has an approximately normal distribution. The standard error of difference depends on the standard deviations of the measurements in each of the population. In the simplest and most commonly used scenario, the two standard deviations are considered to be the same. We need to determine the minimum difference in the means that we are interested in detecting by statistical test. The two types of statistical errors, alpha and beta, and the standard deviation. And so this is the formula for comparing two means. Suppose we want to test a drug that reduces blood pressure We want to say the drug is effective if the reduction in blood pressure is 5 millimeters of mercury or more, compared with the placebo. Suppose we know that systolic blood pressure in a population is distributed normally with a standard deviation of 8 millimeters of mercury. We specify the parameters just like before. And plugging in those values, we get a sample size of 34 in each group. At this point, you probably realize something, that calculating the calculated sample sizes when the underlying distribution is normal are smaller compared to when we are dealing with proportions. We saw that example in the cross-sectional studies, and now we are seeing this pattern repeated here in analytical studies. What if we want to compare more than two groups? Or what if we are using multivariate methods? The formula for these situations are much more complicated. Simple formula for the calculation of sample sizes are not available for multivariate analysis, such as those using multiple linear regression, logistic regression, or comparison of survival curves. But here's an example of one for follow-up studies. So assuming a one-sided test, and for one group, we have this formula. Sample size for diagnostic studies, because these are also studies that are sometimes done. And for this instance, the sample size is calculated in 4 steps using a set of formulas as shown on the screen. In this case, P1, P2 refer to the sensitivity or specificity of the diagnostic tests that we are comparing. Psi is the probability of disagreement between the two tests. That is, one test is positive, the other is negative, under the assumption of maximum disagreement. N corrected is the Yates corrected N, and we need to adjust the sample size for the population prevalence. So an example of this, suppose we wish to compare diagnostic accuracy of malaria rapid diagnostic test with blood film microscopy in children under the age of 5 years. I want to calculate the sample size. And so, from a particular paper, we get sensitivity of RDT at 71.6% and sensitivity of blood film microscopy at 61.6%. And then, following the steps, we apply the Yates continuity correction. And the Yates continuity correction is a standard statistical correction applied to chi-square and sample size calculations for proportions to account for the fact that a continuous distribution is approximating a discrete distribution, and it is particularly important for smaller sample sizes. So by the time we adjust for prevalence, we end up with a sample size of 65. It's important to adjust for disease prevalence, since the disease prevalence influences both the sensitivity and the specificity. So, we come to our conclusion. And what are the key takeaways here? Sample size calculation or estimation or determination balances science, ethics, and resources. We need to master the big 5 parameters. We also need to avoid pitfalls by carrying out sensitivity analysis and adjusting for attrition and loss to follow. We must always validate what we do using software and experts. I end with this quote: an underpowered study is unethical, an overpowered one is wasteful. I'm open to answering any questions that may arise, and these are my contact details. Thank you very much for listening, and these are references which we may consult for further reading. Thank you very much.